This is the demo for Aggregate. I create a database named Aggregate with 4 tables in there. The first table called student grades sorted with the 1200 rows of the data in there. The primary key is on student ID and course ID. The second table called student grades sorted 1 with 400,000 rows of the data in there. The primary key is on student ID and course ID. The third one called student grade unsorted with 1200 rows of the data in there. This is unsorted data, so it has no primary key or indexes at all. The last one called student grade unsorted one with 12,000 rows of the data in there. This is also unsorted data without primary key or indexes. Why we have to learn about unsorted data? Because it's a lot of data out there in the real world which is unsorted or too expensive to sort it. So the query optimizer try to find the cheapest way for us to work with all of those database. From here, the hash aggregate is actually good for the unsorted data, but sometimes users will like, will the query optimizer choose to use hash aggregate with the unsorted data all the time? I can show you in this demo. For the basic aggregation like count, find the minimum, maximum, average, or summation. For the sorted data, you can tell they have like the cluster index in there. What you can guess like what the query optimizer will choose as a query plan for you. When you take a look at the query plan of the sorted data here, you can see that they choose the optimizer will choose to use the stream aggregate for you. With use the cluster index scan for the whole table and do the stream aggregate. But for unsorted data here, when you do the work with the unsorted data and you take a look at the query plan, the query optimizer actually choose to use the hash aggregate for you, which is create the hash table of first do the table scan and do the hash table for you. If you click on here, you can see that for the hash aggregate, the property here, you will see the memory fraction here. That means for the create a hash table, you actually need the extra memory to create a hash table. But if you go back here a little bit to see the sorted data, the query optimizer, the query optimizer here will show the stream aggregates for you. When you click on here, you actually don't see that you need the extra memory here. For this is when you try to do the average of the grade grouped by the student ID. If you run this one, because this data is already sorted, when you do the execution, is the student ID will sort it for you already. But for the hash, for the unsorted, which is you use the hash aggregate. When you do this one, run it, is actually is not guarantee the order. It's just grouped by the student and then do the average of the grade for you. Don't guarantee is we sorted or do the order for you. So but if you want the result with the order by student ID, for this one, maybe you can guess because it's actually the table is actually sorted or has the primary key on student ID and course ID already. So this one if you guess is the query optimizer should choose the stream aggregate for you, um, because it's cheaper anyway. So if you click on that, you can see both even those big data or smaller data. This one has the first one has 1200 rows, the second one has 400,000 rows of the data in there. Both will use the same thing, do the cluster index scan and then do stream aggregate for you. But for unsorted data, this is the one that we really interested in for the for this demo. When you do, can you guess like because is try to call order by student ID. That means you want the result is sorted for you. So for the query optimizer, we'll try to find a way which way is cheaper. Sort it first before do the operation, before averaging, or um, do the hash table, do the average, and then sort it for you later. The for the upper table here, we'll have 1200 rows. For the lower table, we'll have 12,000 rows, which is 10 times of the data in there. So now we will see what query optimizer will choose to use for us. From here, you can see, oh, okay. For the first one with 1200 rows of the data, the query optimizer actually do the sorted for us first. Do the sorted on the student ID first before do the stream aggregate here. But for the second one is bigger data. When you don't want to sort the whole 12,000 rows before do the average. You actually want to spread it or create a hash table and then sort it at the end, because once you do the average already, the rows that you have to sort it is actually smaller, kind of like you want to sort it as less as you can because it's expensive. If you have enough memory, this one is actually will do the hash match, the hash aggregate for you. If you click on here, you can see they have the memory fractions there for you. And this one, okay, you don't need the extra memory. If you run this one, if you actually run or execute this one, you will see here in the property, you don't in the property you don't see the extra memory at all. But when you run this one, we use the hash aggregate for us. When you click here, you can see that for the hash key build here actually need the memory usage here. I will try to show all at once so then you can see the difference here. Okay, this is all. This is for the sorted data. When you want the result that ordered by the student ID, both sorted data, which the query optimizer will choose to use stream aggregate for us. But for the unsorted data, the first one has a smaller data, and the second one actually have larger data. So the smaller one sorted maybe don't really cost that much different than sorted later. So the query optimizer actually choose to use sorted first and then do stream aggregate. But for the larger data, which is the in the real world, you have the big data out there. How to work on that is actually we'll do the hash aggregate for us and then sort it later. So this is the demo of hash aggregate.